In this video, we begin chapter 4 of the textbook. This is over differentiation of functions of several variables. We'll get to the differentiation part, partial derivatives, in a few videos from now. Today, we'll just look at what a function of several variables are and look at a few different terms and formulas that can help us understand what a function of several variables is doing. First, let's look at a function of two variables. A function of two variables is typically written as z is equal to a function of x, y. This function maps an ordered pair, x, y, to a unique real number, z. Functions of multiple variables have a domain and a range, just like functions of a single variable does. The domain is the set of all possible ordered pairs that you're putting into the function, and the range is the set of all values that you could get out of the function. In order to calculate the domain of a function, just think, what can I not put into that function? What restrictions are there on the domain? If it's a rational function, what value can you not put in the denominator because you would end up dividing by 0? If you have a log function, what values could you put inside the log to make what's inside the log a non-positive number? Let's look at an example. We want to find the domain and range of each of the following functions. For part A, f of xy is equal to 3x plus 5y plus 2. Can you think of any restrictions on the ordered pairs x and y that could go into this function? In this case, there are no restrictions. We could put any possible ordered pair x, y into this equation with no problem whatsoever. So the domain of this, we'll use a capital D, is the set of all real numbers. This symbol here, a capital R with two backs, means all real numbers. Since we're free to put anything we want to into the function f of xy, it might stand to reason that we might be able to get any possible z out of this. Well, that's not always true. When considering the range, you want to look to see, is there anything inside the function that would restrict z on the low end, on the high end, or somewhere in between. In this case, if we plugged in a big negative x value and a big negative y value, z would just be a big negative z value. And if we plugged in a big positive x value and a big positive y value, then z would be a big positive z value. There's also no restrictions anywhere in between those extremes. Therefore, we can say that the range of this is also all real numbers. So then, what about part B? G of xy is equal to the square root of 9 minus x squared minus y squared. Z is a square root function, and if we have a square root, we're not allowed to take the square root of a negative value. That means that what is inside of that square root, 9 minus x squared minus y squared, this must be greater than or equal to 0. If we move the x squared and y squared to the other side of the inequality, that would give us 9 is greater than x squared plus y squared. So our domain is x squared plus y squared is less than or equal to 9, which is the set of all ordered pairs that lie along the circle of radius 3, centered at the origin, or also inside of that circle. There's a more formal way to write the domain and range that you should get used to now, and that looks like this. Everything is wrapped inside of curly braces. In this first part, we're declaring what the variables of the domain are, x and y. This symbol is an epsilon, and it means element of. And then this means all real numbers squared. This is a two-dimensional space. So altogether, this just says that x and y are in R squared. This bar means such that. And then we just have how we define the domain, x squared plus y squared is less than or equal to 9. So altogether, we would read this as x and y are in R squared, such that x squared plus y squared is less than or equal to 9. In order to find the range, we need to consider the extremes of the domain. First, let's look at the outer edge of the domain. X squared plus y squared is equal to 9. G of xy was equal to the square root of 9 minus x squared minus y squared. We want to make a substitution using the outer edge from the domain. So inside of g of xy, factor out a negative from the x squared and y squared terms. We can then use that outer edge equation to substitute a 9 into g of xy. That would give us the square root of 9 minus 9, which is equal to 0. So if the edge of the circle is one extreme of the domain, what do you think the other extreme of the domain would be? The edge is the outermost point of the circle, what would be the innermost point? In this case, the innermost point is the center of the circle, 0, 0. So let's plug 0, 0 into the g formula. That would give us the square root of 9, which is 3. That means the range for z would be everything between 0 and 3. And the formal way to write that looks like this. The range is z in all real numbers, such that 0 is less than or equal to z is less than or equal to 3. The next thing we'll look at is at the bottom of page 340 in your textbook, and also at the top of page 341. This is level curves. If you've seen a topographical map before, then you might be somewhat familiar with what a level curve is. The lines on a topographical map show you everywhere on the map that has the same elevation. This is what level curves do. Given a function, f of x, y, and some number c that is in the range of your function, a level curve of a function of two variables for the value c is defined to be the set of all points satisfying the equation f of x, y is equal to c. This is a method for reducing the dimensionality of your graph. If you want to graph f of x, y is equal to z, you would have to plot this in 3D. But if you were to plot the level curves of f of x, y equals z, that would only be a two-dimensional graph. Here's how that works. Suppose that we're given a function, f of x, y, find the level curve corresponding to c equals 0, then create a contour map for this function. What are the domain and range of f? To begin, set your function, f of x, y, equal to c. That would give us this. The goal here is to rewrite this equation into a form that we know how to describe the shape of. Let's begin by squaring both sides to get rid of that radical. That would give us everything that was in the radical equal to c squared. Notice on the left side that the x squared and y squared terms are both negative. I'm going to flip the sign of everything to make those terms positive, and then I'll also group the variables on the left side. Let's factor a 4 out of the x terms. That would give us 4 times x squared minus 2x. We need to complete the square on this parentheses. So negative 2 divided by 2 is negative 1, and negative 1 squared is a positive 1. The value that we added to the left side of the equal sign is actually a positive 1 times 4. So to keep things balanced, add a 4 to the right side of the equal sign. We need to do the same thing to the y's. Add that 4 at the end of the y's. Since we added a 4 to the left side of the equal sign, to keep things balanced, we need to add a 4 to the right side of the equal sign. Next, we can factor the x terms and the y terms like this. And then on the other side of the equal sign, just combine like terms to be 16 minus c squared. This is starting to look like the equation of an ellipse with some constant c inside of the equation. We can get a 1 on the right side of the equation by dividing everything by 16 minus c squared. That would give us this equation, which is going to be the general formula for our level curves in this problem. We're asked specifically to find the level curve corresponding to c equals 0. So then just plug c equals 0 into that general formula. Once simplified, this gives us the equation of an ellipse centered at 1, negative 2. That would give us a level curve that looks something like this. If we want to find the level curve for c equals 2, just plug 2 into that formula, and you'd get this equation. And the level curve for that might look something like the blue ellipse. And if we kept calculating different level curves, we would just end up with a bunch of ellipses of different sizes. To calculate the domain, just take what's inside of the radical and set it greater than or equal to 0. If you do that, then you'll find that the domain looks like this. Then all you need to do is test the extremes of your domain, and you'll find that the range is z and r, such that 0 is less than or equal to z is less than or equal to 4.